thanks for making it back. At least no one deserted me, that's cool. Right, so I just got a feedback here. So for some of you, it may be more desirable to do the earlier one because of the exams that follow the, 2 weeks after the end of lectures, formal lectures, I believe. And I saw that as well. So all the exams are pretty much around 24th, 25th, and onwards. So in your, I'm not sure how much time you plan to whatever for either task, but I would suspect that this weekend will be rather occupied by graphics programming, right? So you won't do much else there. So this would also be, I sense a tendency that people may be inclined just to do it immediately after the course to have it done, which kind of makes sense because, again, you don't need to learn for that exam, you just need to do it, and the best way of doing is continue what you did already, because at this stage you will have just submitted your project for that course anyway, and you can reinforce based on that. Because I won't give you, material to learn as such, you just get the exam and then off you go. Right? So, but anyway, we can discuss that further, but I noted that comment there. So a very valid comment. So 1 week-ish after that one, you're like not even half a week in fact, you will have exams here. And again, this weekend will be occupied. Note that I'm fairly indifferent about whether we do it on from a Saturday to Monday or Friday to Sunday. That's something we can negotiate within class. Probably Friday to Sunday is probably more reasonable because you can occupy your weekend, but then the week at least is free again for the next task you're having ahead, especially if you're looking towards learning for exams and things like that. Of course, unless someone is if you're collectively terribly inclined to do it during the week, that's often an option as well. But I'm not sure if that's on everyone's mind. So no, better not, because it would be really 3 days carved out of your usual obligations. So that's probably better done on the weekend. So cool. We'll reflect on discussion next week again. But see. Think about it. Look at your exam tables as far as out already. I know it's very early, but better early than sorry. What's that one? No, anyway, so not quite. So yeah, better do that as well. Again, right now we're still flexible. That will change eventually. So while we can, let's be flexible. Okay, what I want to get at is we need to do a bit about trigonometry, and that's we just do high school level trigonometry. No magic to do 2D, but just want to get an understanding how the rotations work, unless everyone is clear about it. Did you do it in maths, perhaps? No, whatever. Yeah. Just do it, and you'll see. Yes, clear about it.
Yeah, we have done.
So you know all that.
Yes, do it.
Up to you. So we have the points we're running out of time a bit, so just to get the feel. Anyway, okay, cool. So if we have, for example, a coordinating space. All right, sinus, cosinus, what was it again? Who remembers sinus and cosinus? So given that coordinated space and the corresponding triangle, let's say we have an angle here, that we call that angle. Who wants to give me a Greek letter?
Phi.
Phi is, oh, cute. Okay, right, phi. And we want to actually calculate, find out about any of the components. So, let's start off first. What is the sinus of phi and what's the cosinus of phi? And we probably need to give this some names. Let's call it here R. And this would be the x-axis. This would be the y-axis, and this is actually a dot, not an x. And yeah, okay. So we call that. And that is x 0. All right, cool. Cosinus and sinus of, or sine of phi, please. Like, how would you go about it? Still remember, please?
What's the goal here to find the?
Just to recollect what sine and cosinus is.
Yeah, but on this triangle.
Base or?
Yeah, sinus of phi. Use phi. Yeah.
That one's the bottom right, isn't it?
Again, sorry again. The right angle, you mean?
Yeah.
The right angle is down here. That's. Do you know that notation for 90-degree angles? No. Yes.
We use squares.
Yes, usually it's just square.
Ah, okay. Like that? Okay, interesting. Cool.
Yeah.
Like that? No dot in between? No, just like that? Cool. Sweet. Cool. I'm learning. So that's the way I learn it with this dot thing. That means 90 degrees. Anyway,
Okay.
cool. So now we're on the same notational page. Please, enlighten me.
From what I remember, cosine is the opposite
Yep.
divided by the on the closest one.
Okay. Does everyone share that? So what's your view?
Y0 divided on
Oh, well, this one or which this one?
the sinus is Y0
Yeah.
divided by the hypotenuse.
Yeah, which is R in this case, right? You call those things catheter, right? Or catheter? How do you say it in Norse?
Katet.
Katet. And this hypotenuse. Hypotenuse, katet. Okay, well, same linguistic page here. That's so cool. So right, so okay, sinus is the opposite versus hypotenuse, right? So what's this katet divided by hypotenuse, and cosinus.
X0 divided by.
Cool. X0 divided by R. Cool. So there was the other point about opposite divided by adjacent. What is that?
Tangents.
That's the tangents, right? So we leave that guy alone. We only care about the other two ones here. So that would be y0 divided by x0 for all the stream people. So we just got arrived at this one here. You probably, yeah, don't really see that. Okay, that's the benefit of being on site, right? So it's a big part here. Cool. So we have a rough understanding and can use them. The convenience here is simply that we can use those structures to calculate any of the unknowns that we possibly have in, you know, in rectangular triangle, right? So, cool. All right. So, question now is, assuming that we know that location, so we can, how can we calculate R? In the first place, assuming we know X and we know Y. Famous person behind that whole idea, remember?
Pythagoras?
Square root of x0, the second.
X0 to the power of 2 is what you're saying? Yeah, cool.
Times y0, the power of, or plus. It is plus.
It is plus.
Yeah.
So x to the power of 2. So there you go, right? So basically adding the power of 2, the power of 2 of x0 and y0, and then using the square root should give us the hypotenuse, right? So cool, very good. So we now have the kind of basic trigonometric principles back together. And the person who invented that was, just for everyone, please repeat.
Pythagoras?
Yeah, Pythagoras, or nowadays we call him Python, right? Do we? So anyway, so jokes aside, so different color. All right. So now, question here is, if we want to arrive at that point here, and let's assume we know R, because we have figured out R right now, because we know X and Y, 0 for example. And we basically want to calculate that new position. So we have an additional angle here, which we call creativity, please.
Epsilon.
Epsilon. Epsilon. You're challenging me here. You got me. Then. Epsilon. Yeah, I got it. Okay. Right. Small or big one?
The big one.
Oh, the big one. Okay.
The pretty one.
That's the one. Right? Did I get it right?
I think so.
Let's assume I got it right. But usually you use small letters for angles, I think, right? So it's by convention. So since it's on the stream, I need to be compliant. So we make it really epsilon. But epsilon actually stands for Euler's number, right? By it's a constant actually. Shouldn't use that. No, not good. Not good. but
Sorry.
that's fine. So here's lose gamma. So because it's the only one I know how to draw now. So okay, cool. Challenge. So how do we actually arrive at how do we calculate? Let's assume we know the length of r, but and we know the angle. So how do we arrive at the new position?
Do you need R? You can just use x0 and y0. So do you have...
Well, you don't know x0 and y0 yet. You need to calculate it first.
But right now would be, that's right. So the ones we want would probably be along those lines here. That would be y1, and here would be x1 down here, which is roughly here. Cool. Any ideas? Anyone? No? Just looking it up already? That's good. Found a solution? That's good. All right. So if we convert it, so let's clean up a bit here because it becomes slowly messy. A few things we can probably do now is to got that thing phi, we live with that. And what else would we need to do? Oh, some notes here would help. So now, so if we want to calculate x, we right now we actually need to derive, since the open question is what's x0 and y0, we need to derive somehow x, right? So and for x0 we know that we can do that by calculating by switching the positions here of x and r, right? So we can multiply where I'm losing it right now. Hang on. Picture multiplication times r. So we can multiply cosinus with r to receive a to get x, right? Similarly, we can do the same for the sinus to get epsilon y. So that's cool. So far so good. Have your rough understanding here. So the issue is there. How do we arrive at those values? And the idea is basically that we know a given angle that we want to change the coordinate by, so or rotate it by in a two-dimensional space. So we could do something like cosinus x plus the new angle, which would be beta. I wasn't clever. So unclever as well. X1 is cosinus phi plus beta times r. So r is unchanged. It's just the rotation along the upwards, and for y1 we can do the same. Cool. So that's basically the only thing we need to do. We basically need to include the corresponding angle by which we want to change it into the cosinus calculation. And here's one aspect that may actually be quite handy, is that we have some so-called trigonometric identities. And the idea is there, if we have, for example, have cosinus of two individual angles and we want to reformulate this, we can write it in the following fashion. So we could separate cosinus u and cosinus I, and if it's a positive or additive combination, then it would be negative. and vice versa, if it's a sinus representation, we can multiply the individual sinuses of the individual components and cosinus and combine them in an additive fashion. So that would be the way of converting it. So if we apply that here, let's see if we get that right. So for x, we decided it must be cosinus, so let's do that first. So this one will correspond to sinus cosinus this. And since it's an additive combination, we do the same here. So sorry, since it's additive, we need to do it negative here. So we get that in a second. It's sinus phi times sinus gamma. Roughly right. Cool. And then the same one for the other one. So cool. So we now have sinus. Cool. So that's the individual conversions we need to do. What else I want to say? Cool. Did I get that right? I kind of got that right.
Maybe it's a plus on the first on x and minus on y.
Yeah, the first one is cosinus, so it's a plus, so it corresponds to minus here, right? So it should be about right. Unless
So it's probably right.
There's a totally munted that, which is possibly entirely as well. The only thing that I'm what do I want to do? Give me a second. All right. So if we calculate that with so we have organized them by x1. Do the same for the other one. Not the most intuitive way, I guess. It happens if you sleep like 2 or 4 hours. Okay, sinus times cosinus gamma. Phi times so that's the y representation, so that's the x representation. So cool. So C combine them again.
Will the max magnitude be the same?
X. So there we go. Sorry, what was the comment there?
How does the magnitude stay the same on the last one? The length of the vector. How does that stay the same?
Sorry.
Like the last formula,
Yeah.
we don't have any indication of if the vector is like 1,000 long in x and y, or if it's 1 in length, magnitude.
You're creating a unit vector, right? Like that line is described. The bottom two lines are describing unit vectors, right?
That's right. Yeah.
So you're not
just
specifying the magnitude
you just
of
need to
how
multiply.
far out the x and y points are.
You just,
Right.
you just need
Yes,
to multiply
yes.
by r.
That's right. I'm missing the R component. Yes. Yeah. Thank you. That's right. So thank you very much. That's indeed exactly right. So probably need to phrase it. That's what I'm missing.
I didn't notice.
Thank you.
You noticed.
Thank you very much. Thank you for getting me out of my misery here. So, all right. So we have the R component here. We have an R component here. Similarly here. And there. So that looks a bit better. That's right. So now we can do what we wanted to do, which is actually conversion. So because R times cosinus of the base vector would correspond to 0. Yeah, I probably should separate that out. That wasn't clever here. So we have x0 times cosinus gamma minus y0 times sinus gamma. So that's the representation for that one here. So we're now looking at the x value, x1 in particular. So we can calculate xy now as a multiplication of x0 times cosinus of gamma based on the transformation that we had up here. So we have the cosinus of the input vector, then we get the output there, and minus the same for the corresponding transformation here. So r times cosinus gamma corresponds then to x0, and r times sinus phi, corresponds to y0. So cool. So if we do the same then, let's do the same for x1. So that's the x1. Yeah, I didn't help myself writing it in a somewhat awkwardish way. So when we have y0 times cosinus gamma plus r cosinus x0 times sinus gamma. So, right, if we now use a new board, like this one, cool. So then we can reorganize the components a bit. So we have, for the new, we can write this in matrix form. So we have cosinus gamma, right? That's the x component. And for the y component, we have minus sinus gamma. And for the corresponding x component here, we have sinus gamma, and since they are additively combined, we have cosinus gamma here. So that would be basically our transformation matrix for x and y, to actually have that organized by x and y, right? So the x components are now here, and the y components are now here, of all those transformations down here. And this is the resulting transformation matrix. So if you have any 2D value plus a coordinate, an angle we want to transform over, gamma in this case, we can apply this to our original coordinate and get the target coordinate in that corresponding angle. If that makes sense, I'm not sure. So it was a bit confusing down here. It's easy on paper because you have a big picture perspective. Sorry.
Yeah. Will we be doing manually matrix calculations or vector calculations, or is this just more to understand how graphics are drawn under the hood?
Yes, what you get it is, no, I actually wanted to, I'm not sure if intuitive is probably not the term of choice anymore, but I wanted to get a consistent perspective, since this is super intuitive, right? If we do transformation or translation, basically, just multiply it with a matrix that has change values for the corresponding dimensions. But I personally find it slightly less intuitive for rotations, right? So because we only deal with sinus and cosinus representations, and that might not be super accessible. So I thought doing a simple 2D example just to highlight of how we actually arrive at those seemingly odd matrices, right? So those ones here. And that's basically the only thing you need to know for that one is obviously how sinus cosinus works, and this transformation down here, so the trig identity, where you actually convert different angles. And so the idea is there, now we can everything resolve just based on a gamma component for that tile position. But no, you won't need to do that because we obviously have a function for that stuff, right? And if I'm clever enough, yeah, lucky me, we actually did it down, I did put it down here. So this is how you calculate it. Again, it's GLM. Yeah, that's unclever. I'll read it. I can't read. I notice you can't see it right now, but it's basically you determine the rotation. You indicate the rotation axis, which is either x, y, or z, right? So I'll just probably write it down. My axis, and then you indicate which axis you actually want to rotate over. So it could be, for example, the x-axis, but you actually don't want to rotate over the y-axis or the z-axis. So that you would specify it in this way. And then here's the GLM rotate function that you just need to input the rotation you want to do in degrees and the axis you want to rotate over. Note that the actual input, once you play with that function, is actually not in degrees but in radians, which is like one of the standard units, one of the base units for angular representation. And how you arrive at this one is, so the input for that function is basically this one. So you have your degree value that you're interested in, you multiply it by 180 divided by pi. Yeah, because that's the idea. So one radians is roughly 57 degrees. That's quite straightforward. So once you figure that out once, you're kind of sweet. Please.
Is it not possible to rotate over multiple axes sometimes?
Yeah, that's one option. Yep. You can also apply rotation one after the other, right? So you can sequentially apply them.
Okay.
Yeah, you could first rotate over the x-axis, then rotate over the y-axis. Because what you're basically doing here is calculating the rotation matrix, those ones. And then you can just multiply them with your input vector and do a rotation one at a time if you wanted to. That makes sense? For example, you have a rotation both in, I'll come to you in a sec. We have a rotation over x and we have a rotation over y. Well, if you want to do that, you could do one after the other, right? You achieve the same result.
Yep.
Yeah, sequential operation. Please.
So if you rotate it over, if any of the components in the vector you're rotating over is 2, are you then drawing out 360 or are you doing a 180 then?
No, that's just indicating the axis. It's not the angle. Oh. No, that's just their way of saying, well, I want to only deal with y.
Why are they floats then?
Yeah, because everything in GLM, that's one of the things, if you play with GLM in particular, you pretty much everything has the input type float there. So if you don't do it, you will have weird errors. It's more convention than necessity, I would suspect. So, but yeah, good comment. I didn't think about it even. Yep.
I'm going to assume that you can just rotate, that it lets you rotate over multiple axes, and you can rotate different amounts in each axis by using different numbers.
Yeah, that's right. So you specify x and you vary those numbers and sequentially apply them. Doesn't really matter. That's right. So those were the 3 basic transformations we need to deal with. One special case I want to show you because it's super handy to have and you will really appreciate it eventually. Right now it doesn't make sense. Is the identity matrix, which doesn't do anything. bit like me, it doesn't do anything. But anyway, so the idea is that whatever input vector you actually have when you multiply with the identity matrix, note the diagonal ones, basically multiply the corresponding x, y, and z w value with 1, therefore don't change them, and spit the result out again. When is it good to have? What do you think? Why is it useful to have? Yeah?
You can check if something is similar to the, because if the output is the identity matrix, they are the same thing.
Yeah, but couldn't you just directly compare the input matrix as well? Because there must be the same thing as well if the identity matrix applied to an input vector is the same thing.
I don't remember, but there was something from the last math course we had where you did something and the result was a matrix, and if it was an identity matrix, there was no information there. I don't remember what it was.
Right. Okay. So I give it to you why I find it super handy. It is if you have a combination of different transformations of whatever nature, and you don't necessarily want to specify all matrices, right? Because you want to first perform one operation, then the next one. You can substitute the values for the particular transformation matrix with the identity matrix. So basically, multiply everything by 1. You know what I mean? So you can just leave your equation unchanged, but just use the input matrix for that particular transformation, use the identity matrix, which is initialized like that, and then nothing happens. So meaning for you, from a debugging perspective, super handy to have. So you want to ignore one particular transformation and not confuse yourself. For example, you know, translation or scaling or rotation, want to isolate, then it's very handy just to substitute the corresponding irrelevant transformation with an identity matrix. That's my take on it. It's quite handy to have for that purpose. Cool. So we're running off time, I think. So the issue. So we talked about, and we find that pattern quite often. In fact, translation, rotation, and scaling. And the question is, does the order of execution matter or not? From a conceptual viewpoint, right now, we're doing translation, rotation, and scaling.
No. Because
So
the origin doesn't.
Yeah.
Yeah.
Okay. Well, it depends if it's local or global, especially on rotation and scale.
Yeah.
So if you are doing global rotation, the order matters.
Yep. That's let's let's stay on the object on the individual model level, not global right now. We get global. You're right. You're spot on anyway. But even on the model level, does it matter or not? If we're just interested in our little cube.
When the origin is defined in one of the corners, I'd say it doesn't matter, because if you rotate it first and then translate it, or translate it first and then rotate it, it doesn't matter, because you're not using the axis relative to the cube. So whether you rotate it first, or say you rotate it in the y-axis and then you translate it in the y-axis, you're not gonna translate it in a different direction. Whether you had rotated before or after you translated.
Okay, one position, another position. We have a few different viewpoints. Okay, all right, let's do the following. So let's stay simple. Let's use me as an object. I can't scale, so we ignore the scale operation for now. Let's work with rotation. Actually, I can, but I'm not fast enough. So if we think about rotation and translation, right? So starting from a position, if we perform translation, as I mentioned, it actually changes the origin, right? So if I'm translating myself and assume that is my x-axis here, I'm doing the origin. If I now perform my rotation here, I'm facing a window, and I'm in this origin in this particular position right now. So, but the question is, if I would perform a rotation first and then translate. I may end up in a different position, right? So also, if in fact, one aspect that's also worthwhile. In fact, my rotation was wrong already. If I translate first, I need to rotate around the origin, so it would be a rotation like that. So suddenly there would be change in x-axis from your perspective, as opposed to just being on the spot, right? So model origin, translation, new origin. And then just for the sake of it, rotation, right? Rotation around the translated vector as well. Yeah. So if I just do the transformation rotation first, I would have a rotation here, and then basically my translation afterwards. So we would end up in a different position. So you can't just interchange.
That would be you didn't do the same translation.
Okay. So you're right.
Because first you went to your right and then rotated that way, and then you rotated that way and went to forwards instead of your right. If you went to your right again, you would be here.
Okay.
So that would be the same.
Let's see. If I'm changing my if it's relative to me, yes. But if I perform a rotation, the origin coordinate system is unchanged, right?
No. Well, not if it is the same as the rotation function here. Then it changes everything.
Right. Translation. I perform a rotation around the origin. If I perform a rotation on the spot, then I translate. Yes, I agree. Locally, yeah, but when we're coming to your dimension, because globally it would be different, right?
So currently you were moving in global space. No, moving moving in local and rotating in global.
Right. Yes. Right.
So it really matters.
It matters if do it the right way. Yes, that's right. That's right. So let's fix that. Okay. Yeah.
I was thinking.
Yeah.
If you move forward and rotate right, either you rotate first and then move forward, and you're here, or you move first and then rotate.
That's right. That's why the intuition I want to share. Exactly. So that's the world space perspective. You're right. So sorry for that. Yes. So you need to integrate the world perspective. I agree. So the key problem is the translation bit. Rotation, scaling, whatever, because the origin is unchanged, right? So I increase or shrink in size, or I rotate with whatever axis, but the translation that messes things up in the global viewpoint. Thanks for fixing that. So it does matter. The essence is it does matter. After figuring out half an hour. So we need to bear that in mind. I will wrap that up briefly or quite quickly. You probably need to continue a bit on Monday, because I want to talk about a few more things, because we're actually coming to the world coordinates now. That was the idea. How to actually translate the how do we actually arrive at world coordinates in that sense? But the most important thing probably for today that I leave you with is when we apply this transformation, we need to multiply original vector times first apply the scaling, then the rotation, and then the translation in that order. And that's the order, and it's applied in GLM as well as in the shader language. So that's why I'm emphasizing the TIS operation. So even though it's written in the opposite order, it's actually applied from the right to left. So origin, scaling, rotation, translation. And so if you keep that pattern, meaning if you apply all those three operations and you maintain that pattern, you will always have the same or the correct transformation in your space. So it's quite important. And again, here's my point again. The model origin is the issue, meaning that's world space. If I change my origin of my model in the world, then it makes a difference of what operation I'm doing, where I end up at the end. I think I'll leave it at that, because that was confusing enough. So we now worked on the individual model and did 3 operations on individual models, right? So changing in size, position, direction. And we roughly talked about the order in which they need to be applied in order to not confuse the entire world out of us. Important translation needs to be applied last. The next thing we'll be looking at, not today, is looking at camera perspective with respect to the object, because right now we only cared about the objects in the first place and perhaps about the world to some extent, but we didn't really look about from the observer perspective, right? So each of you has a different camera angle, if you like, and how do we actually bring that into the calculation of the outcome in the end. So I'll probably do that by example on Monday. It's a bit easier because that's something we need to get acquainted with. So we have a lab that actually does that, so where you guys actually explore those functions yourself. Any questions or any comments? Who has no clue what happened here right now? I don't blame anyone, because okay, you guys are good? Good. So it's straightforward anyway. So basically the three functions we're dealing with is literally GLM rotate, GLM translate, and GLM scale. Right? So that's the three functions we need to know about right now. We have the associated matrices that are calculated in GLM. The only matrix that's perhaps relevant for you is the identity matrix that may be useful to substitute any of the transformation matrices. And that's roughly where we are right now. So on Monday I'll show you a bit of code, how to do it. I wanted to get there today, but yeah, it didn't really work out, I guess. But I'll see you in like 5 minutes in graphics in mobile anyway. So see you.
Except for once is going to global.
Yeah.
In home. Yeah,
right, is it today?
Now, basically.
Oh, you're leaving? Okay, yeah, you know.
In an hour.
Go for it. Yes, now of course. Anyway, we'll be streamed, so it'll be fine. But thanks for your attention and yeah, coming here in the first place at 10 in the morning. So.
If we can't wake up to be at school at 10 in the morning, then jeez.
Well, you know, you're the modern day students that are a bit more resilient, you know. In my time, 6 p.m. in the evening is really early, you know, because the supermarket closes. So, but...
Another note, translation in itself is order, I mean, rotation in itself is order dependent. So, if you rotate one direction first and then another...
Yeah, that's right.
You will end up in a different place if you rotate it first one way and then the other.
Okay, hang on.
So,
yeah.
Let's say we are rotating forward and right.
Yep.
So, forward, right. Yep. If you were to rotate right, forward, that's completely different state.
Good point. Good point. You do comment that on Monday. I hope you're here on Monday. You can debug my my statements. So it's good. Thank you. I appreciate it.
I use all of them. Basically, the reason we can actually rotate in midair because you don't have anything to push up, but you can still rotate your body because you're rotating different parts of your body at different rates, and therefore,
right. Yeah. The pitch, yaw, and roll effects, right?
Yeah.
Planes that we combine. You're right. Okay.
Jesus, calm the fuck down, man.